Let's look at question number 7, quite a tricky titration question. So what they're doing is this student has decided, he or she, that she's going to put bromine water into a burette. She's got bromine water into a burette. She's using a drop-in pipette to add 5 drops of oil, and the oil has got carbon-to-carbon double bonds in it, into a flask. It's worrying me that she's using a drop-in pipette and 5 drops of oil. You wouldn't use a drop-in pipette. You'd use a normal pipette. You wouldn't use such a small volume of 5 drops of oil. So that's immediately making me think that there's something wrong with this experiment. But anyway, we've got bromine water in the burette. We've got a very small amount of oil using a drop-in pipette into a flask. The oil has got carbon-to-carbon double bonds in there, and we're pouring the bromine water from the burette into the cooking oil that's got carbon-to-carbon bonds. The bromine water is orange, and when it reacts with carbon-to-carbon double bonds, it goes colourless. So the orange colour from the burette will go into the cooking oil and turn colourless. At the point that all the cooking oil is used up, then the bromine water that's orange will come through into the cooking oil. There'll be no more cooking oil with any more double bonds in there to react, and so the orange colour will start to colour the flask because there's no cooking oil to take the colour out of it, to decolorise it and to turn it colourless. So we're looking for a colour change of orange into the flask as the bromine water comes through and is unable to react anymore. Okay, I've got some volumes here of the bromine water. Let's have a look at the first bit of the question. In the trial experiment, the student failed to fill the burette correctly, so that there's a gap. Suggest the effect. Okay, so you've got the burette here, and you've got an air gap in the bottom of the burette. Well, let's say that the air gap is 3 centimeters cubed. The first 3 centimeter cube that's pouring out of the burette is actually not going to pour out of the burette at all. It's going to fill the air gap. So if we think we've delivered, let's say, 10 centimeters cubed of bromine water from the burette, because the volume's gone down by 10, we've actually not. We've only delivered 7 out of the burette, because the first 3 centimeters cubed went to fill the air gap. So we've only delivered 7, but it seems on the burette as if we'd delivered 10. So, suggest what it would have on the measurement. The measurement is 10, but we've only delivered 7. The measurement is higher than we'd expect. So the measured volume is greater than we'd expect, higher than we'd expect. And the reason is because the bromine water has to fill the gap before any of it's delivered. Other than the incorrect use of the burette suggests a reason for the inconsistency in the student's results. I really don't like using a drop-in pipette here. A drop-in pipette is not an accurate measure of anything. It doesn't measure volume accurately because the drops that come out of a drop-in pipette are all kinds of different sizes. The drop sizes vary from a drop-in pipette, not a good measure of volume at all. Drop sizes vary from a drop-in pipette. Outline how the student could improve the practical procedures to determine the number of carbon-to-carbon double bonds in a molecule of oil so that more consistent results are obtained. Okay, as well as using a drop-in pipette, well, I wouldn't use a drop-in pipette at all, you've got a problem. Because in this flask, you've got 5 drops of an oil and 5 centimeters cubed of an organic solvent. 5 centimeters cubed and 5 drops is a very, very, very small amount. It's going to be very difficult to measure or see the change in colour in that very small amount. And it's too small amount to use. In a flask, when you're doing a titration, you need 25 centimeters cubed. That's the standard amount that we use in a flask so that you can see and measure the reaction change accurately. So first of all, I'd use a larger volume of oil. 5 drops is not enough. Secondly, I'd mix it with the organic solvent. Next, I'd transfer into a larger flask to make up a batch of it, maybe 250 centimeters cubed with more of the solvent. So you've got a batch of the solvent. You always make a batch of chemicals that you're going to use, and then you take 25 centimetre cube samples for the flask. So more oil, 5 drops is not enough. Dissolve it in the organic solvent, make a batch up so it's all the same concentration, and you've made it up at the start and you've got a concentration of that at the right concentration up to 250 centimetres cubed is a good amount to make as a batch, and titrate 25 centimetre cube samples in the flask. That's a more acceptable volume to be titrating against. Let's have a look at this one now, this question here. It's for 5 marks and it's unscaffolded. In other words, it's not led you through, it's not said what steps to take. However, we have some big clues in here. An oil has a density. That word density, there's only one thing you can do with density. Density is mass divided by volume. That's the only equation you've got for density. Density, mass divided by volume. We know we're using that equation, so we've not even got to look any further down. We know density is mass divided by volume. We're going to be using that. Let's do that first. 5 drops of an oil has a volume. Right, so it's given me volume, 5.0 times 10 to the minus 2. Density is mass divided by volume. 0.92 is mass divided by 5.0 times 10 to the minus 2. Density is mass divided by volume, so mass is density multiplied by volume. You're multiplying those two numbers, first of all, to get the mass of the oil. The mass of the oil, 0.92 times 5 times 10 to the minus 2. Now you've got to put a 5 in there as well. Each of the drops has a volume of those, and you're using 5 drops. So that's potentially where you'd make a mistake, because each drop of oil has a volume of 5 and you've got 5 drops. So the total mass of oil you need to times by 5 because you've got 5 drops, 0.23 grams. What's next? Right, I've got the mass of the oil, I've got an MR. So now I need to convert it into moles. The only equation with MR in it is moles is mass divided by MR. So 0.23 divided by 885 will give me the number of moles of oil. Moles is mass, 0.23 divided by the MR 885, 2.6 times 10 to the minus 4. That's the number of moles of oil that I have. What have I got next? I've got the concentration of bromine water. Again, this is leading me in. Concentration is moles divided by volume. Concentration is moles divided by volume. So I'm going to need the volume to be able to work out moles. Where can I get the volume of bromine water? Well, it says I'm using experiment 1. And back here in experiment 1, the volume of bromine water is 39.4. So if I look back in the experiment, I've got 39.4 centimetres cubed of bromine water. I've got the volume of bromine water that I've used. So concentration is moles divided by volume. Concentration moles divided by volume. Moles is concentration multiplied by volume. So I take the concentration, 2.0 times 10 to the minus 2. And then multiply by the volume, which is 39.4, and I'll come out with the number of moles. However, this in centimetre cubed needs to be in decimetre cubed, so I need to divide by 1,000. So 39.4 centimetre cubed is 0.0394 divided by 1,000. That's the volume I use, 0.0394. So, concentration is moles divided by volume, 0.0394 times 2 times 10 to the minus 2 will give me 7.9 times 10 to the minus 4. I now know the moles of bromine water. So by looking at the information I've given, it's led me through the question, and I've got 3 marks already out of the 5. Use this data to determine the number of carbon-to-carbon double bonds. Well, 1 mole of oil reacts with, or should do, 1 mole of oil should react with 1 mole of bromine water, but only if there's 1 double bond in there. So it's actually the bromine water has reacted with the double bond. So if the oil has got one double bond in there, then 1 mole of oil, because it's the double bonds that are reacting, 1 mole of oil with one double bond in there would react with 1 mole of bromine water. However, they're not the same. That's not 1 and 1. If that were the same amount as each other in a 1-to-1 ratio, there'd be 1 carbon to carbon double bond. But it looks like I'm needing a lot more bromine water, 7.9 times 10 to the minus 4, compared to 2.6 times 10 to the minus 4. That means there's not 1 mole of carbon to carbon double bonds in there. If I look at this ratio, 2.6 times 10 to the minus 4 to 7.9 times 10 to the minus 4, if it were a 1-to-1 ratio, there'd be 1 double bond in the oil, but there must be more than 1 double bond in the oil because I'm needing a lot more bromine water, a lot greater number of moles to react with the oil. So what I do is I look at the ratio. The amount of oil that I have, 2.6 times 10 to the minus 4, compared to bromine water, 7.9 times 10 to the minus 4. The reason I need, it looks like I need 3 times the amount of bromine that I do for oil. 3 times. This times 3 comes out as 7.9 times 10 to the minus 4. 2.6 times 10 to the minus 4 times 3 comes out roughly about 7.9. So the ratio is 1 mole of oil to 3 moles of bromine water. That means I need 3 moles of bromine water to react with 1 mole of oil because there's 3 double bonds in the oil. That's why I need 1, 2, 3 moles of bromine water to react with the 1, 2, 3 double bonds in every molecule of oil.